By now, you've written some simple loops and some simple if statements. That means it's time to use more complex logic. To be able to do that, we have to take a look at compound expressions. I guess a good place to begin is to make sure we know what compound expressions are. In simple terms, they're just Boolean expressions formed with the logical operators and, or, and not. In these three languages, you're familiar with those symbols already, but those are high-level symbols, and we're going to have to translate their logic into assembly language. So where are we going to see these compound expressions? Simple. If statements and loops. In this part 1, I'm going to be talking about if statements. Part 2 will cover loops. Let's start with this one. First off, the logical operator here is an AND, which means for the if statement to be true, x has to be at least as big as 7, and at the same time, y can't be equal to 50. Before we go any further, we've got to take a small side trip to discuss short-circuit evaluation of compound expressions. Now basically all this means is that no matter how complex a Boolean expression is, we only evaluate it until we know for sure whether it's true or false. This occurs in the C language, and because C++ and Java are derived from C, it occurs in those languages also. Okay, back to our if statement. Look at the logical operator connecting these two comparisons. It's an AND. Because of short-circuit evaluation, if x is less than 7, the if statement stops, and the program goes to the statement following the if. On the other hand, if x is at least as big as 7, then we're halfway there. We still need to check to see if y is not equal to 50. If y is some number other than 50, then the entire if statement is true, and all the statements inside the body of the if statement get executed. Now let's take a look at how we'd translate this to assembly language. Let's put our if up here in the corner just to remind us of what we're doing. Please understand that when you say x is greater than or equal to 7, what you're really doing is comparing x to 7. In assembly, we're going to use the compare instruction. So when I say compare x to 7 this way, there's really an implied subtraction going on, x minus 7. X is not being changed because the subtraction is only implied. Now here's the important part. Logically, you have to ask yourself, if this first comparison is false, where would I want to go? The answer is to the statement following the ifs. And again, that's because of short-circuit evaluation. Here I'm checking to see if x is at least as big as 7. The opposite is when x is below 7. So I'll use the jump below instruction to jump past the if. Now if it is true that x is at least as big as 7, then we still have to check to see if y is not equal to 50. So that's the next thing we do. I compare y and 50. When would I want to jump past the if statement? The answer is if y is equal to 50. Now you're really going to have to think about this. If I haven't jumped past the if statement yet, that means the compound expression was true. In other words, x was indeed at least as big as 7, and at the same time, y was not equal to 50. The result is we execute the body of the if statement. And last of all, we do eventually reach statements beyond the if statement because after executing the body of the if statement, the next instructions are those that just simply follow the if. If we're good there, let's try one with a logical OR to connect the comparisons. Okay, the logical operator here is an OR, which means for the if statement to be true, either N1 must be equal to 20 or N2 must be less than 100. The logic is different from the AND example. Here, if either part of the if is true, the whole if is true. And keep in mind that short-circuit evaluation of compound expressions still applies. In short, if N1 is equal to 20, we don't need to check the second part. We can skip directly to the body of the if. On the other hand, if n1 is not equal to 20, we still have the possibility of the whole if being true. That is, if n2 is less than 100, the whole if is true because of the OR operator. That means we have to check that condition to know for sure whether or not the if is true. If the second part is false also, then we jump out of the if statement. Otherwise, we execute the body of the if. Let's translate this. Just as a reminder, we'll put this here. Our first comparison deals with n1 and 20. We know that if this part's true, the whole if is true. So we ask, if this first comparison is true, where do we want to go? The answer is to the body of the if because of short-circuit evaluation. But if n1 is not equal to 20, we need to check for n2 being less than 100. Logically, if n2 is either equal to or above 100, we know the whole if is false, and the program should jump past the if statement. Otherwise, the next code instruction is the body of the if. By now, you've seen that those handy curly braces we use in high-level languages don't exist here in assembly. Now, if we didn't make the jump past the if statement, that means the compound expression was true. In other words, either n1 was equal to 20 or n2 was less than 100. The result is we execute the body of the if statement. And last of all, after executing the body of the if statement, the next instructions are those that follow the if. Okay, I've got one for you. How would things change if we added an else to the if statement? Let's use the last example to see. It's no surprise to high-level programmers that when the if part of an if-else statement is true, the code inside the body of the if gets executed. Then the program goes to the statements after the whole if-else. And if the if part is false, the code inside the else gets executed, and then the program goes to the statements after the whole if-else. Let's look at the assembly language translation. The first part is just like before. That is, if n1 is equal to 20, the body of the if gets executed. If not, we check for n2 being less than 100. If n2 is less than 100, the body of the if gets executed. Notice that I'm leaving some space here for the else part. Also notice, and this is really important, after the body of the if is executed, we have to jump over the else code in order to get to the instructions past the if. If we forget this jump, our program will execute both the body of the if and the body of the else. Not a good thing at all. You've never seen that occur in a high-level language. Why? Because the compiler's been doing all this translation for you, and it won't forget to jump over the else code. How does the program get to the else part? Right here. That is, suppose n1 is not equal to 20 and n2 is 100 or more. We're going to jump to the else part of the code and execute the instructions in the body of the else part. And, as before, after the else is done, the next instructions are those that follow the whole if-else structure. After looking at this last example, we get some insight as to how a switch statement might translate to assembly. Here is the basic form for a switch statement. Please notice a couple of things. First, it uses the value of the num variable to decide where to jump inside the switch. Next, it executes the code inside the matching case, and then there is a break to do what? Yeah, to jump out of the switch. Third, if you use the optional default, its code is the none of the above fallback option. Here's a question. What happens if you forget the breaks in the different cases? Oh yeah, the code falls through to the lines of code in the lower parts of the switch until either there is a break or until the switch ends. Does that sound familiar? In the last example, if we forgot to jump over the else, then the code below the body of the if executes too. If we translated this switch to a series of if-else statements, it would look something like this. Coding this if-else ladder in assembly would be very similar to the if-else example we already looked at. You'd simply have to extend how many else sections you have and when to jump to them. And as part of each body, you'd have to jump over any remaining else parts to a point past the whole structure. If you really think about it, a switch is really just a compound expression where all the parts are connected with ORs. Which brings us to the end of part 1. Each example dealt with a situation where your program could branch somehow. Part 2 will look at translating high-level loops into assembly. Thank you for watching this.